Welcome to the walkthrough for the skeletons, specification, and unit tests for assignment 2B. The objectives of this part of the assignment are to learn how to synchronize Java threads via core synchronizers, including a recursive mutex, which is a Java reentrant lock, as well as a semaphore, which you'll implement using a Java reentrant lock and a condition object. Videos describing the relevant Java synchronizers appear in the various videos linked below. I recommend you watch these videos to ensure you understand these synchronizers. Naturally, we cover these topics in class as well. In this part of the assignment, you'll use a semaphore that you implement as well as a Java reentrant lock to enhance the executor service thread pool implementation of the Palantiri simulator app from assignment 2A. Assignment 2B focuses on the Palantiri manager, which is used to restrict the number of beings from Middle Earth who can concurrently gaze into a fixed number of Palantiri. This app is packaged as a project using the latest version of Android Studio. The app's written in both Kotlin and Java and demonstrates many interesting Android capabilities. However, for this assignment, you'll need to be aware of three directories: the manager's Palantiri reentrant lock hashmap simple semaphore directory, which contains the skeletons you'll need to fill in, as we talk about in a minute; the app source test directory, which is a set of JUnit tests that exercise many features and can be used to help automatically test the functionality you implement for the assignment; and the app source Android test directory, which is an Android Studio implementation test that runs your app automatically. You'll need to integrate your solution for the executor service folder from assignment 2A into the latest greatest executor service skeleton and use it as an implementation for the being manager in assignment 2B. Please make sure you address all my comments on your assignment 2A solution before using this code as the basis for assignment 2B. To compile the code, you'll need to use the provided Android Studio project. This is no different from before. You have to click the Run App button to run the test after you've compiled it, and that'll prompt you to select an emulator. And if you haven't created an emulator yet, you can create one by using the ABD Manager button on the Android Studio IDE. But I think at this point, you should have that all set up. As always, you'll need to modify several files containing skeleton Java code by completing the to-do you fill in here tasks to provide your working solution. Please don't change the overall structure of the skeleton, just fill in those tasks. You'll have to implement the to-do tasks for a number of files in the reentrant lock hashmap simple semaphore folder. You'll have to implement the simple semaphore.java file, which contains various methods you have to complete to define a counting semaphore with fair semantics that you'll implement using a Java reentrant lock and a condition object. You'll also have to implement the reentrant lock hashmap simple semaphore manager.java file, where you'll have to use your simple semaphore, a reentrant lock, and a hashmap. If you're taking the class for grad credit, you have to implement certain methods using Java sequential streams, as we talk about below. And then finally, you'll have to complete the to-do portion in the assignment.java file to set the S-types field to indicate whether you're taking the class for grad or undergrad credit. As always, if all the unit tests and instrumentation tests pass and everything works correctly, then your program will be considered correct. And as before, you'll get visual feedback indicating how the Palantirian being states are proceeding, how the progress is going, and if everything goes well, you'll have green labels, but if something goes wrong, you'll get red title bar labels that indicate that your simulation has failed to complete correctly. Graduate students or students who are taking the class for graduate credit have to perform the following additional task. You have to use Java sequential streams in several places in the reentrant lock hashmap simple semaphore manager.java file. Undergrads are welcome to implement these Java functional programming enhancements, but it's not required. As always, you can download the skeleton code for this assignment from my GitHub account. Now that you've set up your GitLab account, just go ahead and pull my skeleton code into your repository, read it carefully, and complete the to-do markers. Any additional work required by grad students should be clearly marked. This part of the assignment is designed to get you familiar with synchronizing multi-threaded programs using core Java synchronizers that are more powerful than the spin locks we covered in assignment 1B. It doesn't require you to program any Android concurrency frameworks, which we'll cover in upcoming assignments. Now that we've walked through the specification, it's time to explore the skeletons. As you can see here, you go into the managers folder under the simulator folder, and there's a couple places to look. There's beings and there's Palantiri. Obviously, beings is what you did for assignment 2A, so make sure you copy your working solutions for executor service and runnable threads under beings based on assignments 1A and 2A, and then come down here to Palantiri And of course, you should have your solutions for the spin lock hash map manager solution from assignment 1B, just so you can have that available. But this time we're going to focus on the reentrant lock hash map simple semaphore folder. And that's the one that we're going to see here. So we'll start looking at this in just a moment. Now that we've talked about the specification for this assignment, let's go ahead and look at the skeletons, starting with simple semaphore. This class defines a counting semaphore with fair semantics, and we use the Java reentrant locking condition object classes to implement this particular abstraction. There are 3 fields you have to implement to start with. First, you'll have to define a field that is used to keep track of the number of available permits, and make sure you properly qualify this field to ensure that its values are never cached when used by multiple threads. So if multiple threads read or write to it or update it and so on, you'd never want to have those changes be cached in the processor caches. That should always go directly to main memory. So that's a big hint. Next, you go ahead and define a field that will be a lock used to protect the critical section, and make sure that that's the lock type. Likewise, you want to define a condition field that's used to wait while the number of permits is 0 or less. In this particular case, make sure you define this with the condition type, and those are the 3 fields you have to fill in. You don't have to worry about the simple semaphore default constructor that's provided for you. You will, however, have to implement the simple semaphore constructor that takes account of the number of permits. And here you'll have to go ahead and initialize the field that keeps track of the number of available permits. You'll have to initialize the lock, making sure that the lock you create is a reentrant lock with so-called fair semantics. And you'll also have to create a condition using the reentrant lock and its appropriate factor method that makes a condition associated with that lock. The first method you'll have to implement is the acquire method that actually does the protocol for semaphore. This will acquire 1 permit in a manner that can be interrupted. So you can see it can throw the interrupted exception. The way this works, of course, is you have to ensure that you acquire the lock, you lock the lock to make sure you're in a critical section, exclusively getting access to the internal state of this object. You'll then have some kind of a loop that's going to loop while the permit count is less than or equal to 0. And whenever it's less than or equal to 0, you're going to go ahead and use the condition to wait. And when it wakes up, it'll come back around again and check to see whether or not the condition is to its liking. Once you make it past that guarded suspension check, then you can go ahead and decrement the count by 1 and make sure you release the lock on the way out in a manner that never fails, even if an exception occurs. Acquire interruptibly is similar to acquire, except the difference here is that you don't let this method be interrupted. So what you'll do is you'll do many of the same things. You'll acquire the lock. You'll have a loop that checks to make sure that you're going to have a permit count that's greater than 0. And if it's not, you'll wait. But in this case, you're going to catch any exceptions that occur, set a flag, and then loop back around again and keep doing this. You'll never break out of this loop as long as an interrupted exception occurs. So what'll finally happen, of course, is eventually you'll get through it without being interrupted, and then you'll unlock the lock and make sure that you also set the interrupt flag. So you want to make sure that if an interrupt has occurred, and only if an interrupt has occurred, you'll set the interrupted flag and the interrupted status so that a caller knows that an interrupt occurred, even though it still managed to acquire the semaphore without being interrupted. The next method you'll have to implement is release. And what you do here again is make sure you've got mutual exclusion by using your lock. Then you'll go ahead and increment the count. And if incrementing the count causes it to go greater than 0, meaning that there is a possibility to let other waiting threads move or go ahead to acquire successfully, you'll then go ahead and signal the condition. As always, on your way out, make sure you release the lock. And then the final method here is just going to return the number of permits. If you set the qualifier on your field correctly, all you have to do is just return that value, because it'll do an atomic read from memory and will not require any further synchronization. So that's an overview of the simple semaphore class. So that's the first thing you'll have to implement. Then you'll also have to come along here and you'll have to implement the reentrant lock hash map simple semaphore manager class, which extends Palantir Manager. As you can see here, you're going to have to use your simple semaphore in order to limit concurrent access to the number of available Palantiri that this Palantiri manager manages. You'll also have to use a lock here, which is the lock interface. So you'll make a field there that's the lock interface. And then down here, you'll have to fill in some accessor methods to make the unit test work properly. And then you'll have to fill in the build model virtual constructor. And as you can see here, you have to, a hash map is created for you. And then you'll have to go in and, depending on whether you're using the grad version or the undergrad version as your implementation guide, you'll have to implement the right semantics. So you'll have to go ahead and create your semaphore using the simple semaphore implementation that you provided, given the appropriate number of permits, which of course is a function of the number of available Palantiri. And then you'll have to go ahead and initialize the reentrant lock and make the reentrant lock use unfair semantics. The reentrant lock that is used to protect the Palantiri manager can be unfair, whereas the reentrant lock that's used for the simple semaphore has to have fair semantics. So those are the initializations that you'll have to do. And the grad students have to do the initialization using a Java sequential stream. Undergrads are free to use a sequential stream, but you don't have to. And we've talked about this in previous frequently made mistakes videos. So go back and watch that and see how not to do it, which should give you a hint on how to do it. The acquire method is the one that's going to actually get a Palantir from the Palantiri manager, blocking until one is available. This, of course, is going to use the simple semaphore that you define above in order to wait until you get access, until there's a Palantiri that's available for you, a Palantir that's available for you. And then what you do here is you'll use the reentrant lock to guard access to the hash map. And the hash map logic should be very similar, if not identical, to the hash map logic that you did in assignment 1B, where the difference is that if you're a grad student, then you have to use a stream to do this, whereas with undergrad students, you're free to use a stream, but you don't have to. You can just use the for each loop like you did before. As we did before, make sure that you properly release your lock using the try finally idiom, and make sure that you keep that semaphore acquired across the call to acquire. Down here is the release method. This is where you're going to give back the Palantir to the Palantiri manager. As before, always do a sanity check to make sure you haven't got a null that's being passed back incorrectly. Make sure that you properly acquire the lock, as always, in this case, the reentrant lock. Make sure that you put the Palantir back into the hash map using either replace or put. Make sure that you check the return value to make sure it gave the right result. Store that in a Boolean. And then in the finally part of the try finally block, make sure that you go ahead and release the lock, and then conditionally release the semaphore if everything worked properly when you put the Palantir back into it. So again, a lot of this code is very similar to assignment 1B. You just are using a reentrant lock here and your simple semaphore instead of using a spin lock and the Java semaphore. And then finally implement the code that returns the number of available permits, which should be a no-brainer once you look carefully at your simple semaphore implementation. And that's basically the code walkthrough. Now that we've walked through the specification and looked at the skeletons, I'll show you how to run the unit tests. As always, you click down into the tests folder and then essentially right-click on Run Tests in Java, and that will go ahead and open up the tests. As you can see, once they're built, they go ahead and run automatically. We have quite a number of tests at this point because we're running tests for the previous implementations as well. And as you can see here, as it completes, as usual, we'll be testing to see how things work for assignment 1A, assignment 1B, assignment 2A, and now assignment 2B. And if all goes well, as was the case here, everything should have a green check mark by it. You can see there's lots and lots and lots of tests. There's tests for the simple semaphore, which you implement for this assignment. There's tests for the reentrant lock, hash map, simple semaphore manager, and a bunch of other tests as well, stress tests, normal tests, integrated tests, and so on and so forth. And so if all goes according to plan, everything should be green, and you'll get some So I have diagnostics printed out here indicating how things work and how long they take to run and so on. But the key thing is to ensure that when you're all done, you get a check mark and all the tests should pass. Make sure you run your tests. Please do not fail to run the tests. If you run the tests and you get errors, then you, of course, want to come and either try to fix them yourself or feel free to come to office hours. But I can't stress enough how important it is to run all those tests.